Good day. For those of you who do not know me, my name is Douglas Harder, and this topic we're going to discuss normal operators. So in this topic, we will define what it is for a linear operator to be normal. We will investigate how such linear operators and their adjoints affect the lengths of vectors, and we will see that the null space and the range are identical for both a normal linear operator and its adjoint. Starting with a definition, a linear operator mapping a vector space to itself is said to be normal if it commutes with its adjoint. So A times the adjoint of A is equal to the adjoint of A times A. This is actually not normally true. For example, here's a very simple matrix. A is the square matrix 0, 1, 2, 3. If we calculate A times its adjoint, and for real matrices the adjoint is the transpose, so A times A transpose is the matrix 1, 3, 3, 13. However, if we calculate A transpose times A, we get the matrix 4, 6, 6, 10. Now, you'll notice that both A times A transpose and A transpose times A, they are both symmetric. However, they are not equal. Theorem: every linear operator that is self-adjoint and every linear operator that is skew-adjoint is normal. Proof: well, suppose that a linear operator is self-adjoint. Therefore, A equals the adjoint of A. Consequently, A times the adjoint of A is just A times A, which is A squared, which is equal to the adjoint of A times A. Thus, a self-adjoint linear operator is normal. Similarly, if the adjoint of A is negative A, then A times its adjoint is negative A squared, which is exactly what you get if you multiply the adjoint of A times A. Thus, a skew-adjoint linear operator is also normal. Therefore, as a consequence, every real symmetric matrix is normal. Every real skew-symmetric matrix is normal. Similarly, every matrix that is complex that is also conjugate symmetric is normal, and every complex matrix that is conjugate skew symmetric is also normal. There are other matrices that are neither symmetric nor skew symmetric but are nevertheless normal. For example, here we see the following permutation matrix, and yes, indeed, it is normal. Also, this matrix here, which is the first matrix plus the identity matrix, that matrix too is normal. In fact, any linear combination of a normal matrix and the identity matrix must also be normal. You can prove that for yourself. Theorem: if A is a normal linear operator, then the 2 norm of A times U is equal to the 2 norm of the adjoint of A times U for all vectors U in the given vector space. Proof: well, the 2 norm squared is just the inner product of A times U and A times U. However, note that I can bring the one linear operator over to the other side by taking its adjoint. So this is equal to this expression here. But we assumed that A is normal. So the adjoint of A times A is equal to A times the adjoint of A. Now I have something on the right-hand side that is A times a vector. Well, therefore I can bring that linear operator A back to the left-hand side by taking its adjoint. Oh, but this is just the inner product of the adjoint of A and itself. So this is the 2 norm squared of the adjoint of A times U. Therefore, taking the square root of both sides, we see that the 2 norm of A applied to U is equal to the 2 norm of the adjoint of A applied to U. Note that this is not actually true in general. For example, given this matrix A, which is 0, 1, 2, 3, a 2 by 2 matrix, then if I multiply A by the vector 1, 1, I get the result 1, 5. Now the 2 norm of 1, 5 is the square root of 26. On the other hand, the adjoint of A is its transpose. So if I multiply the transpose of A by that same vector, I get the vector 2, 4. And the vector 2, 4 has a 2 norm of root 20. Again, you can see that these are not necessarily equal. Indeed, in some cases, a vector may be in the null space of the linear operator A, while not being in the null space of the adjoint. Now, if A is a normal linear operator, then the null space of A is equal to the null space of the adjoint, and the range of A is equal to the range of the adjoint. This, of course, isn't always true. For real square matrices, this means that the null space of A equals the null space of the transpose of A, and the range of A is equal to the range of the transpose of A, if, of course, A times A transpose equals A transpose times A. Proof. Well, if A applied to U is equal to the 0 vector, then the 2 norm of A applied to U is equal to 0. However, from our last theorem, we just saw that if A is normal, then the 2 norm of A adjoint applied to U must also be equal to 0. But if that's true, then the adjoint of A applied to U is equal to the 0 vector, because the 0 vector is the only vector that has a 2 norm of 0. Therefore, U is in the null space of A if and only if U is in the null space of the adjoint. So for real square matrices, U is in the null space of A if and only if U is in the null space of the transpose, if the matrix is normal. Thus, the null spaces are equal. For the next part, we're going to give more a sketch of the proof. So if U is in the null space of A, which is equal to the null space of the adjoint, then A applied to U equals the adjoint applied to U, which is equal to the 0 vector. Now, the inner product of the 0 vector with any vector in the vector space is equal to 0. So both of those inner products must be 0 for all vectors v in the vector space, because the first component is the 0 vector. But now let's use a sleight of hand. Let us bring the linear operator onto the other side. So what this says is that U inner producted with the adjoint of A applied to any vector v, that must equal U applied to the adjoint of A applied to any vector of v, but the adjoint of the adjoint is equal to A, so that means also that U inner producted with the operator times v is equal to 0 for all v. Now, if that is true for all v, then the range of both A and the adjoint of A is simply the image of that operator applied to every vector in V. Consequently, that means that the vector u in the null space is perpendicular to the range of both A and the adjoint of A. Thus, each vector in the null space is perpendicular to all vectors in each of the two ranges. Now, for finite dimensional vector spaces, and that's all we will prove here, the dimension of the null space plus the dimension of the range is equal to n, and the same for the adjoint. Consequently, because both of the ranges are perpendicular to the same null space, and because the dimensions of those ranges must be, first of all, equal, and they have to complete the vector space, because they're perpendicular, they must be the same, and therefore the ranges are equal. Now let's take a look at this matrix, which we saw before was normal. Again, if we apply Gaussian elimination, we get this solution for the homogeneous system of linear equations. Okay, from this we deduce that a basis for the range are the first two column vectors. Additionally, solving for the zero vector, we get that a basis for the null space is the vector 1, 1, 1. You will notice that the vector 1, 1, 1 is perpendicular to both of those other two vectors. So therefore, the null space is perpendicular to the entire range. Now, here's the transpose. If again we solve the system of the homogeneous system of linear equations, then once again we find that the first two vectors form a basis for the range. Also, once again, finding the null space, we determine that the null space is the same. It is all scalar multiples of the vector 1, 1, 1. And once again, we also see that that vector is perpendicular to both basis vectors for the range. Now, looking on comparing the two ranges, we see that the second vector of the first basis is equal to a scalar multiple of the first vector of the second base for the range. And the first vector of the basis on the left is simply the sum of the two vectors for the basis on the right. So consequently, those two ranges are indeed equal, and as we can see, they are perpendicular to the null space. Now in this case, I moved the 1 at entry 3, 1 to entry 2, 1. So this matrix is close to, but not identical to the previous matrix. However, this matrix is not normal. Solving the homogeneous system of linear equations, we get that a basis for the range are the first and third vectors, which is sort of obvious because the second column is a scalar multiple of the first. Also, if we solve the homogeneous system of linear equations, we get that a basis for the null space is this vector here. You will notice that the null space is not perpendicular to either of those two basis vectors. Here's the transpose of the matrix. Again, now we try to solve the homogeneous system of linear equations, and we get that a basis for the null space are the first two vectors. Okay, yeah, those are different subspaces altogether, as you can see. Also, if we solve the homogeneous system of linear equations, we get that a basis for the null space is a completely different vector. It's the vector 1, 1, 1, which is not overlapping the other null space, except for, of course, the 0 vector. So, as you can see, also the second null space is only perpendicular to one of the two basis vectors. Following this topic, you now understand what it means for a linear operator to be normal. That is, A times its adjoint is equal to the adjoint times A. You understand that all self-adjoint and skew-adjoint linear operators are normal, but that there are others as well. You also know that for normal matrices, the 2 norm of A times any vector is equal to the 2 norm of the adjoint times that same vector. This is not the case in general. You also know that if a linear operator is normal, then the null space and the range for both A and its adjoint are identical. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!